Hello students, we are starting a new topic. The topic is triangle congruence. And we're going to spend about 3 weeks on this topic. It's also a question on the final. We're going to ask you, what do you know about triangles? And you'll have a chance to tell us. So the first section in topic 4 is congruence. What do we remember about congruence? What shapes have we said are congruent so far? Well, we have had a bunch of shapes. Points. Points is the most basic shape. Are points congruent? No. Points are not congruent because they don't have a size. They're infinitely small. So one of the shapes we talked about early on was a line segment. So there's a line segment AB, and we can measure it with a ruler. And if we can say it's 5 steps to get from A to B, and if we have another line segment that is also 5 steps, maybe it's line segment CD, we can say that line segment AB is the same size and shape as line segment CD. They're congruent. What's another shape that we can measure? That's right, another shape we talked about measuring was an angle. Here's a nice big fat obtuse angle. I'm going to call it angle T, naming it by its vertex. And we could get a protractor out and measure it. And I could find that it's 110 degrees out of the 360 degrees in a circle. And if I have another angle sitting over here, maybe it's kind of a reflection, call it angle U. If I get out a protractor and measure that one, it's also 110 degrees, then we can say that angle T is congruent to angle U. It's the same size and shape. Another way to talk about congruence and sort of prove that two shapes are congruent is if you can take your shape and transform it through a rigid motion to get it to match up on the new shape. So another way to think about congruence is that you take your shape and you do something to it. You reflect it, or you rotate it, or you translate it and get it to match up on top of the other one. So we can say in this problem that triangle ABC is congruent to triangle DEF because I can reflect it over line M. Remember, the capital R stands for reflection. In this notation, you can take a look. We take triangle ABC, we reflect it over line M, and it's going to match up perfectly with triangle DEF. So we're allowed to say that triangle ABC is congruent to triangle DEF. Notice that triangles are made up of things that we can compare. We can compare the line segments, and we can compare the angles because triangles are made up of line segments and angles. All right, here's a math problem. It says basically, how could you get triangle ABC to match up onto triangle A prime, B prime, C prime? And the word for that is map. How could you map triangle ABC onto triangle A prime, B prime, C prime? Well, in order to do that, you can just choose one point and think about how could I move A so that it would match up on A prime. This one looks like a straight slide. Okay, do you remember what that's called in rigid motions? Is it a reflection, a translation, or a rotation? Good, it's a translation. So I'm just going to slide it over. I'm going to translate it. Remember, we use our pointy brackets here. Okay, so we have A. Rosie, you need to be quiet. And we're going to move A. Hi, come be quiet. Come here. Come. We're going to move it 1, 2, 3, 4, 5 to the left, and 1, 2, 3, 4, 5 down. So it's going to be, remember, our X is changing by 5, and in this problem, they happen to be the same. What are we doing that to? We're doing that to triangle ABC. And what does that give us? It gives us triangle A prime, B prime, C prime. Okay? So we have, this is how you would write it. And because that's true, because that's a rigid motion that can get them to match up, get it to map onto the other one, then we can say that the triangles are congruent. This is a proof of why this statement is true. Okay, let's look at another one. Oh, this one looks a little more interesting. So this time they're telling us that triangle XYZ is congruent to triangle ABC. And we have to give the composition, the mapping that would get triangle XYZ onto triangle ABC. So we're going to start with triangle XYZ, and we're going to do two things to it this time to get it to match up onto triangle ABC. And it's really important, the order is important. So after we do our transformation, point Z has to land where point C is. So I could just move Z3 to the right, but then the rest of the triangle wouldn't be in the right orientation. So I'm gonna have to do a little bit more than that. How are we gonna get point Z to point C and bring the rest of the triangle along? So there's lots of ways to do this. I kind of think that there's gonna be a rotation involved here. And it's not always easy to see it right away. You might have to play with it a little bit. If I rotate it 90 degrees, that would get it to here. And if I spin the whole thing around, and if we're in class, I would actually get some tracing paper out and we could trace it and actually move it. Because I'm a kinesthetic learner, that would be a really easy way for me to do this. So I'm trying to prove that triangle XYZ is the same as triangle ABC. All right, let's look at a little hint here. Oh, interesting. So it says let's rotate it and then move it over. So let's look at that together. So if we rotate, and we haven't done any like this, but what if we rotate around point Z? What if we spin it 180 degrees around point Z? So that's gonna spin the triangle so that it lines up. 1, 2, 3, 4, 1, 2, 3, 4. It's gonna look like that. It's a little hard to see, but if I spin this, if I spin from here to here, 180 degrees. And this time I'm just spinning it right about point Z. So it's just whoop. Okay, this Y is gonna land over here. And this X is gonna land over here. And we want X when we're done to match up onto point A. Okay, so we spun it 180 degrees. Are there other ways to do this? Yes. Okay, is this one way to do it? Yes. Okay, and then I still need point Z to land on C. So it still needs to go 1, 2, 3 to the right. So here is how you could write this. We're going to take triangle XYZ and we're going to do a composition of transformations of rigid motions. So the first thing we're going to do is we're going to rotate around point Z. And oops, I did that wrong. Oh, what did I do, you guys? I did a reflection. I need a rotation, lowercase r. And I'm going to go 180 degrees about point Z. After that, I'm going to translate it. And I'm just going to move it 3 to the right. And 0 up and down. Okay, this is a 0, not an O. Okay, and when I do that, remember I do it in reverse order. So I do this first, and then I do this. That's going to give me triangle ABC. All right, looks a little complicated. This is a proof of why these triangles are congruent. You can see here it's a little nicer, and you can see the rotation of 180 degrees around point Z. And then you can see to get the blue one onto the triangle APZ, you would just slide it over 3. All right, here's another one. Oh boy, how are we going to get triangle GHJ onto triangle KLM? How are we going to get triangle GHJ onto triangle KLM? Oops, yeah, KLM. Okay. So again, there's lots of ways to get from one to the other. I think I'm going to save this one as a challenge. Okay, we'll talk about this one more another time. Let's look at this one. We have triangle ABC, and we have triangle EEFG, and we have triangle JKL. And the question is, there's 3 here. Which ones are congruent? Okay, we have one way to do this is actually just look. To get from A to B, I have to go up 4 over 1. So the distance of this is going to be the square root of 17, I think. Okay, because I went up 4 over 1. Yeah. So are there any other triangles that have a segment that's this same distance? Okay, now if I look over here, this is up 2 over 3. That's not the same length. This is straight 1, 2, 3, 4. That's not the same length. Okay, and this one's obviously kind of longer. So let's look at this triangle. Oh, here we go. We have from E to K is up 4 over 1. So this length right here is also the square root of 17. So it looks like AB and JK are the same length. Okay, that's a clue that these triangles are probably congruent. I can check this side, that looks right. This length, maybe 1, 2, 3, 4, 5, 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2. So one way to look at this is do the parts match up. These 2 triangles look like they're congruent to me. Yeah. So how could I prove it? How could I get triangle ABC to match up on triangle JKL? This one looks a little easier to me. I'm going to slide the triangle straight down, 1, 2, 3. Okay. I'm gonna redraw this triangle straight down 3. And it's gonna look like that. Ooh, it's kind of messy, but it's good. Okay, so that's my new C. And remember, I'm trying to get C to match up onto L because the order matters. This triangle is not congruent. So I'm going to show that this triangle is congruent to this triangle. And so far, so good. I have C a lot closer to L now. Okay, do these triangles look like they're the same size and shape? Yeah. And how could you get C onto L? What would you have to do to this triangle to get it to match up on this triangle? Good, a lot of you are seeing it. It's a reflection. I'm gonna flip it over this line right here. Okay. So it's I'm gonna take the whole triangle and just flip it right onto there. And when I do that, C is gonna land on L, and B, 1, 2, 3, 4 away from that line, 1, 2, 3, 4 is gonna land on K. Okay, and A is really far away from this line of reflection, and J is the same farness away. Because it's 1, 2, 3, 4, 5 to get to that line, and it's 1, 2, 3, 4, 5 to get out to point J. Okay, so I have my plan. I'm gonna take triangle ABC. And what was the first thing I did? I translated it. I moved it down. How much did I move it down? I moved it down 1, 2, 3. So I didn't move it left, right. I just moved it down 3. And next thing I did was I'm going to flip it over that line. I'm going to reflect it. And I could name this line M, or I could use let's just do that for now. And I'm going to name it line M. For those of you who are a little more advanced, the equation of line M is x equals -4. Okay, so an alternate way to write this is to write the equation of line M. Okay, either one would be fine. And when I do that, I get triangle JKL. So why are they congruent? They're congruent because if I take triangle ABC and slide it down 3 and flip it over this line M, it's going to match up perfectly. It's going to map onto triangle JKL. Oh, look at how beautiful this is, okay? The next thing you could do is you could write a congruence statement and then list all 6 pairs of corresponding parts. So what does that mean? The congruence statement is that triangle ABC is congruent to triangle JKL. The next thing is to make a list of all 6 pairs of corresponding parts. Whoa, that seems really complicated, but it's really easy. Angle A is going to match up onto angle J. That's one part. Angle A is going to map onto angle J. Angle B is going to end up the same size and shape as angle K. And angle C is going to map onto angle L. And a really easy way to do this is to look at this. A and J are in the first letters, B and K are the middle letters, C and L are the last letters. Okay. The other parts of triangles have 3 angles. That's why they're called triangles. They also have 3 line segments. They have 3 sides. So AB, side AB, that's this one, is the same. Side AB is the same as side JK. It's the first 2 letters of each, okay? And you can see, well, that's what we talked about already. They're the square root of 17, both of them. And then I can take the next 2 letters. So line segment BC matches up perfectly with line segment KL. Line segment BC is the same length as line segment KL. And the longest side here, the longest leg of the triangle is from A to C. So this time I'm taking the first and the last letter. And over here, it's going to match up with the first and the last letter. So that matches up with triangle J, or side length JL. So this is all 6 congruent statements. Triangles have 6 parts in them. They have 3 angles and they have 3 sides. Okay, that's the lesson for today. Be good, do your homework. Have a good day. Sorry for the barking dog.